Hi guys, welcome to CMOS IC design lesson. Today's topic is about fabrication of CMOS IC, showing you how the IC is manufactured. First, I'm gonna show you how a single silicon is formed. There are three silicon crystal structure: single crystal, polycrystalline, and amorphous. This picture shows an overview preparation of silicon wafers from crystal growth all the way to the wafer inspection. This ultra-pure TCS is subsequently vaporized, distilling the TCS achieves an even higher level of purity, dilute with H2 and load into a deposition reactor where it is transformed into elemental silicon. This polysilicon has typical contamination levels of less than 0.001 ppb. Now that the high level of purity has been attained, 99.99999% 11 nines, the atomic structure of the silicon must be dealt with. The polysilicon mechanically broken into 1 to 3 inch chunks and undergoes immediate surface etching and cleaning in a clean room environment. These chunks are then packed into quartz crucible for meltdown at 1420 degrees Celsius in a seasoned furnace. A process known as crystal growing transforms polycrystalline into silicon into samples with a singular crystal orientation known as ingots. Oxidation creates silicon dioxide layer. This function of a layer is silicon dioxide SiO2 on a chip is multipurpose. SiO2 plays an important role in IC technology because no other semiconductor material has a native oxide which is able to achieve all the properties of SiO2.
Doping by which a silicon atom is lactic from silicon are replaced with atom dopant. Phosphor and arsenic are used to develop an silicon. Next, boron, gallium, indium is used to p-type silicon. The function of dopant layer is to control the sensitive silicon. Predicate to flow current carrier. Next, there are three methods doping. First, terminal diffusion, ion infiltration, and amplification. Terminal diffusion was accomplished by exposing the silicon wafer dopant, then driving into the wafer with high temperature by diffusing. Diffusion. Two-step diffusion process. First, diffusion and drive in. The wafer exposed to dopant, and next, the wafer heated along the temperature about 100 to 120. In the time temperature amount the dopants are under control, improve the semi-management above the surface. Drive in. No more dopants provided. Drive the dopants from the surface into the wafer to depress it by control the temperature and time. Thermal diffusion, advantage and disadvantage. Advantage is ability to reduce very high concentration of the dopants into the polysilicon layer, attaining low value of resistivity. Disadvantage, thermal diffusion, the high processing temperature and tendency to increase the surface roughness. The next method for doping, the ion implantation. Depositing dopant into the polysilicon layer by directly covering it with the high energy ion in the dopant species. The method can produce a dopant layer with the highest sensitivity of dopant. There are two parameters which can be controlled, which is tip of the area dop, density of doping material. Advantage and disadvantage ion implantation. The accuracy of dopant precision and density can be controlled with high precision. Thickness of dopant is uniform. Use allow temperature in the room. Atom will dopant it directly into the wafer surface. Reduce the crystal damage by high temperature. The advantage cause the defect to crystal lactic base by dopant atom. High cost equipment producing of wafers is limited. Next, about process etching. Definition: material removal. Curve and metal using acid. Etching is a process which a material is removed from select region or substrate. Remove layer materials as silicon oxide, silicon nitride, and polysilicon that are not required in particular place on wafer surface. Etching process in perform component of wafer. These materials are only required in certain area only. Each etching process only remove on one type material only. Etching, objective etching, to remove photoresist and oxide layer on the wafer surface in the photolithography process. To remove surface damage during the cutting wafer. To remove jagged effect around the wafer. Remove metal layer which are not required in the metallization. In etching, there are two types, which is wet etching and dry etching. Wet etching is the liquid chemical, high sensitivity with respect to marks and substrate. Used to manufacture a circuit with the feature size larger than 3 micron. Etching react the chemical reactive gas or plasma. Used to define the circuit feature smaller than 3, greater to control over the process parameter, temperature, gas flow, and power. Etching. There are 3 situations after the etching process. First, normal, over etch, resting, lifting. Comparison between wet and dry etching. Method, chemical solution. For dry etching, plasma and ion format. Advantage for wet etching, low cost, easy to implement, high etching rate, good sensitivity for most material. And then next, for the dry etching, capable to defend the small feature size. The advantage for the wet etching is potential of chemical handling hazard, and dry etching, low throughput for sensitivity, potential radiation damage.
Hi guys, sup! Today I'm going to show you the 20-step CMOS fabrication process. Okay, for the step 1 is the primarily start the process with P subtraction, and here you can see the P subtraction for the early of the CMOS fabrication. Okay, for the step 2 is oxidation, and you can see here the oxidation process is done by using the high oxygen and hydrogen, which are exposed in exudation furnace explosivity at 1000 degree centigrade. Okay, and the step 3 is the photoresist, and what you can see here, photoresist is the layer at the top of exudation, and unlike synthetic polymer that often whatever exposed to light is called photoresist layer, and it is the form. What you can see here, masking. Masking is the step 4 for the CMOS fabrication. The photoresist is exposed to UV ray through the anvil mask, and here the explanation and the picture of step 4. And the fabrication and step 5 is photoresist removal. A part of photoresist layer is removed by treating a wafer with the basics or acidic the solution, and here the explanation. Okay, and the step 6 is removal of SiO2 using an acid etching. The SiO2 oxidation layer is
removal through the open area meant by the removal of photosynthesis using hydrofluoric acid. And here the explanation, and you can see here half of the P substrate is removal. Okay, the step 7 is removal of photoresist. The entire photoresist layer is stripped off as shown in the picture here. What you can see. Okay. Okay, step 8 is formation of the end well. By using ion implantation of diffusion process, end well is formed. And here the explanation. Okay, steps 9 is the removal of SiO2 using the hydrofluoric acid. The remaining SiO2 is removed, and what you can see here, all the layer on the top is removed, and the only thing that leaves is fabrication and end well. Okay, this is the step 10 of CMOS fabrication, and we call it deposition of polysilicon. Chemical vapor deposition, or we call it CVD process, is used to deposit a very thin layer of gate oxide. And what we can see here, the P substrate and end well got the layer, the top layer, it's we call polysilicon. And I think this is my last explanation of step 10, and I let my friends to explain it. Okay, bye bye.
Okay guys, now we are going to step 11. In step 11, removing the layer bearing in a small area for the gates. As you can see. Okay, for the step 12, oxidation process. Next, an oxidation process is formed on this layer with two small regions for the formation of the gate terminals of NMOS and PMOS. Okay, step 13, masking and end diffusion. By using masking process, small gaps are made for the purpose of end diffusion. The N-type dopants are diffused or ion implanted, and the three N-type are formed for the formation of the terminal of NMOS. Step 14, oxide stripping. The remaining oxidation layer is stripped off. Next, for the step 15 is P diffusion. Similar to the above N diffusion process, the P diffusion regions are diffused to form the terminal of PMOS. Step 16, thick film oxide. A thick film oxide is formed in all regions except the terminals of PMOS and NMOS. Step 17, metallization. Aluminum is put on the boil water. Step 18, removal of excess metal. The excess metal is removed from the water layer. Step 19. Step 19 is terminals. The terminals of the PMOS and NMOS are made from respective gaps. For the last step, step 20, assigning the names of the terminals of NMOS and PMOS. And next is fabrication of CMOS using P-well process. Among all the fabrication process of the CMOS, N-well process is mostly used for the fabrication of the CMOS. P-well process is almost similar to N-well, but the only difference in P-well process is that it consists of a main N substrate, and thus P-well itself acts as substrate for the N device.